So to get to the next stage in our study of rings, what we want to do is look a little bit deeper into the structure of rings by talking about what are the sub-objects inside of rings that we're going to care about. This happens pretty much any time you study a mathematical object. As soon as you study sets, then you start thinking about subsets. As soon as you study vector spaces, then you start thinking about vector subspaces. You study groups, and you start thinking about subgroups. So now when we're studying rings, you might think that we're going to pay a lot of attention to sub-rings. In other words, subsets of a ring, which are themselves rings under the same operation. But there's kind of a technical example or two that show why subrings are maybe not exactly the object that's going to be the most flexible for us. It turns out that the kinds of sub-objects we're going to care more about this semester are not sub-rings, but are called ideals inside of rings. So first we're going to look at an example that illustrates why subrings might be a little bit funny to work with, and then we'll talk about what is an ideal, what makes an ideal a principal ideal, it's the analog to cyclic in the world of rings, and then look at a few examples of ideals inside of rings, both principal and non-principal examples. So why do we not care about subrings so much? Well, sort of the very blithe answer here is that sometimes the addition and the multiplication operations inside of a ring don't get along inside of a subring the way that we might like them to. So really the best way I have to illustrate that is with a quick example. Let's just take a look at the example of the cross product of the ring of integers with itself. Okay, so these are just ordered pairs of integers with component-wise addition and multiplication. And then look at the subset, which consists of those pairs for which the second entry is equal to 0. So S is Z cross 0 here. So what can we say about the ring Z cross Z? Well, Z cross Z is a commutative ring because addition and multiplication of integers is commutative. It also is a ring with unity because it has an identity element 1, 1. Right? That's the multiplicative identity in the ring Z cross Z. Meanwhile, the subring S, it actually is a subring because it's a subset which is itself a ring under the same addition and multiplication operations. It's also a commutative ring. It also has an identity, a multiplicative identity element. But the multiplicative identity element in S is not the same as the multiplicative identity element in the bigger ring Z cross Z. In S, the multiplicative identity element is 1, 0. So some weird things can happen if we look at a subring, because we might get some properties that don't line up in a subring with the properties of the bigger ring itself. So there's some potential weirdness here. So we're not actually going to care too much this semester about subrings. What we're going to care about instead is a different kind of subobject called an ideal. So what is an ideal? Because our rings necessarily are not commutative, they could be commutative rings, but they might not be, we have separate definitions for what it means to be a left ideal and a right ideal. So here's the first part of the definition. An ideal is first and foremost a subset, and that subset is an additive subgroup. In other words, this subset has to be closed under the addition operation of the ring. So it's an additive subgroup of R. And the second requirement is not that it be closed under the multiplication operation of R. That would make it into a subring. Instead, we want it to be closed under multiplication by even by elements outside of the ideal. So it absorbs multiplication not just from elements of I, but also from elements of R. So if A belongs to R, then A times I is a subset of I, or I times A is a subset of I, depending on whether we're talking about a left ideal or a right ideal. So an ideal is a subset, which is an additive subgroup, and it also absorbs multiplication from elements of R. The canonical example that motivates our study of ideals comes from the integers, as most examples from ring theory do. So here's the integers, and I've highlighted the multiples of 3. So again, this is the subset of integer multiples of 3 that we looked at a couple of videos ago. And it turns out that this subset is an ideal. Why? Well, first of all, it's an additive subgroup, because if I take any two multiples of 3 and I add them, I'm going to get some other multiple of 3, so that part works. And it also absorbs multiplication from elements of R. R in this case is the integers, Z. So what that means is if I take an element from I and any other element from the ring of integers, so 6 and 2 for instance, so 2 doesn't belong to I, but if I multiply 2 times 6, I do also get another element of I. So this is an additive subgroup, and we can also multiply by any integer at all and get another element of this subset. So this actually is an ideal. One of the most important ways of generating an ideal is by picking so-called generator, and this is completely an analog to how you generate a cyclic subgroup in group theory. Any ideal which is generated by a single element from the ring is called a principal ideal. So this is the ring analog to what a cyclic subgroup is. And when this is the case, we denote the principal ideal in the same way we denoted a cyclic subgroup, just by using angle brackets around the element which we call its generator. So thinking back to the example that we saw just a moment ago, the integer multiples of 3, we saw that this was an ideal because it was an additive subgroup and because it was closed under multiplication from the ring of integers itself. But it has as its generator, for example, 3. Why? Because, well, look at the additive subgroup generated by 3. That's going to consist of all of the additions of 3 with itself, and also the inverses of those additions. So it's a generator of the additive subgroup, which is of multiples of 3. Of course, this ideal we could also have chosen a different generator for. Negative 3 also generates this subgroup in the same way, and therefore this ideal in the same way. So this is an example of a principal ideal in the integers. It's the principal ideal generated by the number 3. All right, let's get our hands dirty with some more examples of what ideals look like. So inside the ring of integers, 6z, the multiples of 6, is also an ideal, for the same reason as the ideal 3z was in the previous slide. So that's, again, it's a principal ideal with a generator 6. But let's look at another example where we might not necessarily have an ideal that's principal. So let's take a look at 4z plus 10z. So this is going to be the sum of the multiples of 4 and the multiples of 10. So let's take a look at what that looks like, starting by visualizing what 4z looks like. So here's the set of all integer multiples of 4 on one line. Meanwhile, 10z is the set of all integer multiples of 10, so we'll look at that on a separate line here. So 4z and 10z. And then my question is, how can we take these two different principal ideals, 4z and 10z, and stick them together and get the ideal that we're thinking of, which consists of the sum of the multiples of 4 and the multiples of 10? Well, one idea might be to just stick them together with a union. I've highlighted the union elements here. But the problem with taking the union of two ideals is that that union doesn't necessarily even have to be an additive subgroup. For instance, 8 belongs to this union and 10 belongs to this union, but their sum, 8 plus 10, doesn't belong to this union. So this isn't even an additive subgroup if I take the union, and therefore the union of these two ideals is not even an ideal at all. So the ideal J that we're thinking of is definitely not the union of 4z with 10z. Alright, so if union didn't work, how about intersection? If I take the intersection of 4z with 10z, and just overlap them here, it turns out that I get 0, and I get 20. I would get negative 20, I would get 40, and so forth and so forth. In other words, I would get every common multiple of 4 and 10. And I would end up getting an ideal. I would get the ideal generated by the number 20. But that's not really the ideal that we mean here, because what we wanted is we wanted to be able to add multiples of 4 to multiples of 10. So this is still an ideal. So the intersection of two ideals is an ideal, but it might not be the one that we're thinking of here. So instead, let's ask this question. What do I get if I take the ideal generated by 4 and the ideal generated by 10 and I add those two as sets? In other words, add every multiple of 4 to every multiple of 10. Do I get an ideal? And if I get an ideal, what ideal do I get? So what does 4z plus 10z look like? Well, we know it's going to include every element of 4z and every element of 10z, so it includes the union. But it also includes other things. It includes, for instance, 4 plus 10z, so everything which is congruent to 4 modulo 10. So that includes 4, but it also includes 14. It includes negative 6. It includes negative 16, and so forth. It would then also include 8 plus 10z, which includes 8 in addition to 18, and negative 2, and negative 12, and so on. It includes 12 plus 10z, which we're going to pick up 22, and we're going to pick up 2, and we're going to pick up negative 8, and so on. And it also includes 16 plus 10z. And by the time I've gone through all 4 of those, cosets of 10z, if you like, take a look at what I've highlighted. I've actually highlighted every single even integer. So it turns out that the ideal which we get by adding 4z and 10z together is exactly the principal ideal generated by the number 2. So even though it looked like this ideal had sort of two different so-called generators that comprise this ideal, it turns out not really to be the case. Really, this is a principal ideal generated by 2. In fact, and this is a fact you would have to prove using a little bit of number theory, every single ideal inside the integers is a principal ideal. The integers are what's called a principal ideal domain. Okay, what do ideals in the rational numbers look like? So if I take the principal ideal generated by, I don't know, 3/16, then what does this ideal look like? I'm going to claim that this ideal gives me all of the rational numbers. In other words, that I don't miss anything. To prove that, well, it's obvious that I is going to be a subset of the rational numbers because that's where it lives in the first place. So what we need to show in order to prove this claim is that the rationals are a subset of I. In other words, every rational number belongs to this ideal. So I'm just going to pick any old rational number, and then I want to show that that rational number belongs to I. So let's let y be a rational number, and we want to show that then there exists an x such that y is equal to 3/16 times x. Well, what x can we choose? All we have to do is over on our scratch paper solve this equation for x, find out x is equal to 16/3 times y, and since y is rational and 16/3 is rational and the rational numbers form a ring, then 16/3 times y is also rational. Now back in our proof we'll say choose x to be 16/3 y, and we know that's a rational number. Then we know that y is equal to 3/16 times x. QED, that means y belongs to I. So the ideal generated by the number 3/16 is all of Q. In fact, we can make an even stronger claim. Because the rational numbers form a field, fields have no non-trivial proper ideals. So this is not too difficult to prove, but it does show us that really rings are something more interesting than fields in certain respects. So we can have an ideal inside of a ring which is not trivial and which is not the whole ring. But once we have enough properties in that ring, namely, once we have the properties that make it into a field, namely commutativity and division ring, then there are no non-trivial proper ideals inside of a field. What about polynomials? These are our main interest this semester. So let's take a look at the principal ideal generated by t inside of the polynomials over t. So that principal ideal is going to consist of all the polynomials which are divisible by t. In other words, these are going to be the polynomials whose constant term, whose constant coefficient, is equal to 0. So for instance, t to the 4th plus 3t, 18t to the 12th minus 15t squared, 6t, these all belong to I. But things like t to the 3rd plus 1, 11x to t to the 6th minus 11t plus 12, negative 8, those don't belong to I. So anything with a non-zero constant term won't belong to I. Now let's look at the ideal j, which has kind of these two different polynomials in it, t and t squared plus 1. So if we think of j as the set of polynomials that are both divisible by t and divisible by t squared plus 1, then t cubed plus t and anything which is a multiple of t cubed plus t will belong there. But anything which is not a multiple of t cubed plus t will not belong to j. So this, again, if we think of this as the intersection of the ideals generated by t and t squared plus 1, then that intersection is a principal ideal generated by t cubed plus t. Finally, let's look at an example of an ideal that's not, in fact, principal. And in order to get such an example, we actually have to go up a little further in our study of rings and think about the ring of polynomials in two variables, x and y, say with integer coefficients. And we're going to look here at the ideal, which is the sum of the ideal generated by x and the ideal generated by y. The question is this a principal ideal? First of all, what does this ideal look like? Well, it's going to consist of everything which is the sum of a multiple of x and a multiple of y. So for instance, x squared y plus xy squared belongs to this ideal, because it's x times xy plus y times xy. X squared plus y cubed belongs to this ideal because it's x times x plus y times y squared. So x times a polynomial plus y times a polynomial. That's what the elements in this ideal look like. But the claim is that this is not actually a principal ideal. Let's think about y for a second. Well, the multiples of x, so all polynomials that are divisible by x, belong to this ideal. Likewise, all polynomials divisible by y belong to this ideal. But what do those two principal ideals have in common? The intersection of those two principal ideals. They have nothing in common. The only polynomial which is both divisible by x and divisible by y, the intersection of those two, I guess that's not actually true, is it? So really, this intersection is going to be the polynomials divisible by x times y. But our claim, again, is that I is not a principal ideal. And to prove why not, well, imagine that it has a generator and that generator is a function only of x. Well then, if the generator is a function only of x, then I can only generate functions of x with that generator. So I'm going to miss out on all the y's. Likewise, if my generator is only a function of y, then I'm going to miss out on all the x's. But then also, if my generator has both x's and y's in it, then it turns out I can't generate something as simple as just plain x, which I know belongs to this ideal. So this is an example of an ideal that's not principal. And in general, most ideals in the world out there in the wild are not principal ideals. But it turns out that making a principal ideal is just a very simple way of making an ideal to work with in general.